Welcome to lecture 5 of the course Mind and Brain. In this lecture we'll look at an improvement of functionalism, you could say. We'll look at the theory of connectionism.
In our historical overview of the answers that have been given to the question how the mind fits in the physical world, we have seen quite some theories. Some should be rejected, like dualism and idealism. They should be rejected because they don't take science seriously. Behaviorism should be rejected because it doesn't take the mind seriously. And that means that we'll end up with a materialist theory. Materialist theory, that is a realist theory about the mind, so it takes the mind seriously. It uses the best method we have to answer questions, that is the scientific method, and it then ends up with accepting mind-body supervenience. The physical world determines the mental world. The mental world, for its existence, depends on the physical world. But then the question is, which materialist theory is the right one? We've looked at the identity theory. There's a lot in favor of the identity theory, but the problem was the mind seems to be multiply realizable. In the end, that boils down to the assumption that you could have other animals than human beings with minds, and since they have different brains, the mind is multiply realizable, or even that computers might be able to think, or alien life with a different structure and different stuff and being made out of different stuff. So they might also have minds, and that means that the mind is multiply realizable, and we've then seen that if that's the case, identity theory cannot be correct, or so the argument goes. So that's the problem for the identity theory, based basically on the assumption or the plausibility of the claim that the mind can be realized in multiple ways. And that problem is, of course, enhanced. It becomes bigger, it becomes worse if there is a theory that is taking science seriously, takes the mind seriously, can use all the scientific evidence that is in favor of the identity theory, but also can explain how mental states might be multiply realizable. Functionalism does do that, at least for the cognitive part of the mind. We'll take a look in next lecture, in one of the next lectures, whether that's actually also the case for qualia. But functionalism had a problem that is biologically not very realistic. It has a model of realizing a mind that uses serial processing, so it has a low damage tolerance, and also it seems to leave out meaning of thoughts, and thoughts seem to have meaning. So that's the Chinese room argument, or the conclusion of the Chinese room argument by John Searle. So we want something better. We want a theory that takes the mind seriously, that takes science seriously, that also looks at the possibility that other animals have minds, which makes sense, I think, so that it also takes multiple realizability seriously, and it should be biologically realistic. It should have it should portray a model that it has is more tolerant to damage than the model in functionalism, and it should in some way explain how our thoughts can mean something, can have semantics. So semantics should not be left out of the theory. Today's theory, connectionism, is supposed to do all that. And in order to understand it and understand the implications of it, we'll have to go back to lecture 1 for a moment. Brief recap. Do you remember what propositional attitudes are? So think about it before you look at the next slide. So pause the movie for a moment. What are propositional attitudes and what are the properties of propositional attitudes? Take a moment. So what is a propositional attitude? Since we need this later in this lecture, I will explain it again. So it's an attitude, a stance towards a proposition, and a proposition is the meaning of a sentence. So it's the concept of an entire sentence. So we have a sentence like, it's snowing, and it has a meaning. And this meaning is the proposition. And this meaning is the same. This proposition is also expressed by the Dutch sentence, het sneeuwt. So then we say, well, the sentence is between two quotation marks and the meaning is written down and referred to by using the same sentence but then in single quotation marks. So, and we can have different stances, different attitudes towards those propositions. You can know it's snowing, you can hope it's snowing, you can believe it's snowing. So believing, hoping, knowing, those are attitudes. There are stances you can have towards a proposition, the meaning of a sentence. And what is one big important property of the propositional attitudes? One property that's really important is that that propositional attitudes are discrete entities, entities that are not connected, so discrete to other things. So that means that they don't really have influence on other things if they appear or disappear. So take a look at an example from outside of the mind-body debate. Beans, for instance, if you have a bag of beans, then beans are discrete entities. So if you have one bean, if you take it out of the bag, that doesn't do anything to the other beans, doesn't really matter. And if you put one extra in it, it also doesn't really matter. And the same would go for propositional attitudes. If you learn a new propositional attitude, if you acquire knowledge, then that is something that is like a bean in the bag. It takes up some space in the bag, some space in your brain, but it has a separate location. It's not connected to the rest. It doesn't influence the rest. So you can also forget it again. So if you learn that Tilburg University is located at Warhandelaan 2 in Tilburg, you say, oh yeah, I knew I could go there, but I didn't know the exact address. Now you've learned something new, you have acquired this propositional attitude, you now know that Tilburg University is located at Warhandelaan 2 in Tilburg, and you might forget that. In a couple of weeks you might say, oh yeah, he told me, but I forgot. Does that mean that you forgot other stuff? No, it doesn't influence your other beliefs and your other knowledge, according to this classical analysis of what propositional attitudes are. Today we'll see that that is well, being debated in this view we will discuss today, this view of connectionism. It might have implications for how we think about propositional attitudes. So that's what we said when we had our initial classification of those mental states, the three mental types we had: experiences, cognitive states, and emotions. Of these cognitive states, propositional attitudes are the example in philosophy of mind. If you look at many texts, at least of a couple of decades ago, then if we're talking about cognition, we are talking about propositional attitudes. And what we said then is, okay, we have this initial classification, but maybe later we need to adjust that classification. But it is a classical classification of the mental types. So we started with that, and today we'll see that maybe we need to, well, adjust this a little bit. That's how science works, that's how critical thinking works. If you have some initial beliefs and you'll find out something later about the world that pertains to those beliefs, you might have to change them. So let's look at connectionism. Connectionism is an alternative to functionalism. So we're still addressing this question, can computers think? So last time we saw functionalism. Yes, it is a theory that's supposed to be about the entire mind, but clearly, if you look at the examples, it's only about cognition. We leave the problem of the qualia, hence the experiences and the emotions, to lecture 7. So connectionism is supposed to be an alternative for functionalism with respect to at least thinking, with respect to having thoughts that have intentionality, that are about something. And of course, after we will explain what connectionism entails, we have to see where that leaves us. Is it indeed a better alternative, and what do we need to look at in the next couple of lectures? Connectionism is an improvement of functionalism. It's a materialist theory. It takes science seriously. It accepts mind-body supervenience, and it's biologically more realistic. At least that's the idea. So let's take a look at connectionism and see whether that actually is the case. Connectionism, in brief, is a view on artificial intelligence, on information processing, that deviates from the classical idea that information processing is a serial process. So it's not a serial, but a parallel process. Information is not processed step by step, but all at the same time. So other terms that are used for this way of modeling the mind, modeling the brain, are parallel distributed processing, PDP, and neural network theory, and of course it's artificial neural network theory, because we're not only talking about biological neural networks. So it is in line with functionalism that says, well, okay, it at least is a theory about cognition. It enables us to make machines that might have cognitive minds. It is a materialist view. It takes science seriously. It takes the mind seriously. Well, if you can make minds out of different stuff, it takes that part of multiple realizability seriously. Well, the question is whether it is also taking multiple realizability seriously, or accepts it or believes that it is true as it as a claim about structure. So we'll take a look at that in a moment. But in general, it's just an alternative to the classical approach of intelligence and cognition and information processing. The classical approach is that information processing is step by step, is serial, and the new approach is that information is processed in a parallel fashion. I'll explain in a moment what that is. We are interested in connectionism as a philosophical thesis about consciousness. So connectionism can be seen, of course, also as what the scientists do and the theory they have that actually build connectionist network, that make these artificial intelligent networks that can perform all these cognitive tasks and process information in this parallel way and not in a serial way. So that is one point, and of course philosophers look at that. We'll see some examples of that. It's all introductory, so those examples will be very easy. But in the mind-body debate, we are interested in connectionism as a philosophical thesis about the mind. So the Churchlands, Paul and Patricia Churchland, they can be seen as philosophical connectionists. So they don't build these connectionist networks themselves, but they take a look at what these scientists are doing, what their assumptions are, and what the results are, and what we might learn. So the idea is that they argue that the brain is a neural network. Well, no quarrel there, right? So we all will agree on that, and Jeroen is going to tell you much more about that. So if you're not aware of that right now, you will be after this course. And if we want to build an artificial brain, well, obviously we're going to use different material, different stuff, different components, but we should try to stick as close to the architecture, the structure of the brain, so the way the brain is made, as possible. So that seems to be a restriction to multiple realizability. You say, well, we're looking at multiple realizability. Yeah, we do accept that. But let's first take a look at how the brain is structured, and if we can make something like that, if we use different stuff but the same structure. So stay as close to the architecture as possible. And then, of course, the interesting thing is, if we make a very simple structure, because we haven't made a brain by far, so these scientists have made very simple structures, and already the results from that are so magnificent, and they have impact on how we think about the mind, how we think about how the mind fits in the physical world. So that is what connectionist philosophers do. They look at this science of connectionism and infer from that conclusions about the mind-body relationship. So that's what we are interested in. Okay, so looking at the brain, very simply, the brain consists of neurons, a lot of kinds of stuff, but the neurons are important here. The neurons are connected to each other, they signal each other, they fire to each other, they send signals. So we have these biological units in a neural network, and it's a neural network, well, of neurons. Those biological units are called neurons. So in the brain part, Jeroen is going to explain you all about that. So neurons are connected to each other and they form a network. So it's not that one neuron fires to the second and then the second to the third and the third to the fourth, etc. and that is just a long line of neurons. No, one neuron can send signals to different other neurons, and so it's a network. And that already takes us to the idea that a brain processes information, not in this step by step way from one neuron to another, but in a parallel way. That you say one neuron sends signals to different other neurons, and then you have already parallel information processing. A connectionist network consists of units. The units are artificial neurons. They are depicted here as circles with a letter in them. So A is an artificial unit. A is connected to G, for instance, and it can send a signal. If it gets some input, it can send a signal to G, and from G it goes, for instance, to L. If this is the only thing that would be going on, then we would be talking about serial processing, right? So then there's some output from L. So that would be serial processing, and of course there is serial processing going on here. But the interesting thing is that A also sends a signal to H or to I. And that's what parallel processing is. Information coming into the system is processed in multiple ways simultaneously. But if we look at the strength of the signals, they might differ. The more of the connections between A and G, for instance, and the connection between A and H, they might be different. So it's not that if there is input coming in A, say it has a value, all inputs have a value between 0, no input, and 1, maximum strength, maximum input. So in A, for instance, there is input coming in from 0.7. Then it could just send that input to G. So then it's 0.7 to G, but it could send 0.6 to H and nothing to I, for instance. So it can amplify things. So to K, for instance, it might send a signal from as strong as possible, 1. So there are different weights between A and G. So there are different strengths, you could say, of the signal. So then you could say A is a bit like a volume on your stereo, for instance. If you have an old-fashioned stereo, you have this dial for the volume from 0 to 10, and A is kind of functions as a kind of a dial from your amplifier of your stereo. So there is a signal coming in from say your CD player. A signal from the music is coming into the amplifier and it goes to your speakers, and you can amplify that to 10 really hard, something in between 5, 4 and 0. You could send no signal to your speaker. So you could say, well, you could compare that to the weight, and then you say, well, the weight between A and G is on a scale from not from 0 to 10, but from 0 to 1 is 0.4. And another weight between A and H might be 0.4, and between A and Y might be 1. So you have different settings, different weights for the different connections. And a scientist making these models can change those weights. So basically, we have these the AI, artificial intelligence units, neurons, and they receive and send. They receive input and send output. And the important thing now here is that they are not only processed, not only connected in this serial way from A to G to L, but also from A to G and from A to H and from H to Y and from D to I and from D to K, etc. So there is this parallel connection. And then we have, usually in a very simple network, we have input units. They send to one layer of hidden units, the internal units, and then they send a signal to the output units that provide us with an output. So for instance, you can look at it, especially the input units. It's clear they are located at the surface of our body. So for instance, the nerves that you use to feel that you have a cup in your hand, or the retina. So there's light falling on the cells of your retina, and of course there are cells in your retina. They get stimulated by the light and they send a signal to the back of your brain, but that goes in steps. So L might be a neuron in your visual cortex. So that's the idea. And A does not only send immediately a signal to L, no, it goes via other layers of neurons, and in the end it gets there. But A also sends to H and to other, indirectly then does to other neurons in the visual cortex. Okay, so this is the basic, this is the simple idea, and of course connectionism is, and has different varieties, and it's really can be really complex, but these are the basics. So it is about the basics for this course, and that you already see that if you just look at the basics, you can already learn something about our question, how the mind fits in the physical world. We get an answer, or we get a partial answer to that, and it's a different answer from the answers we so far have seen, and it's also an answer that you might not have expected. Let's look at some examples and see how it works, and then we'll take a look at the philosophical implications of the findings of a scientist that made these really primitive, these simple neural networks. So let's look at logical neurons. So it started with that, and here we add something to it. That is, we add that units have a threshold. So you have input coming from 2 or 3 or 4 other units. So A, B, C, and D all fire to E, and only if there is a certain amount of input of all the units together that it reaches a threshold in E, and then, only then, if that threshold is reached, then E will fire. And for the moment, we'll just we'll just use 0 and 1. There is either no input or there is input. There's no scale in between. So the idea is that every function in proposition logic, so that's a type of logic that investigates propositions, sentences, in which we use and or, so these logical operators, the notion of and, the notion of or, they can be implemented in such a connectionist network. Let's look at and. So you're saying, what do you like in your coffee? Milk and sugar. So then if you get coffee that has milk in it but no sugar, then you say, that's not what I ordered. If you have coffee that has sugar in it but no milk, then you say, that's not what I ordered. And if you get a black coffee, that's also not what you ordered. You only say, okay, I accept this this coffee only when there is milk and sugar in it, so both. So we're going to look at a very, very simple network with just 2 input units for milk and coffee, or for Tony and Ronnie, if you want to make if you want to talk about were they both present at your meeting or something like that. And one output unit O that says, yes, there's milk and sugar in my coffee. Tony and Ronnie were both present at my meeting. So both input units send a signal to the output unit. So that's the parallel way. So there's input coming simultaneously and going to the output unit. And this output unit has a threshold of 2. So we're talking about only about no input versus input. And then, of course, you get input from unit 1 and input from unit 2. And only if they both fire to the output unit, then the output unit should say yes. Then it should provide output and basically says yes, there is milk and coffee in milk and sugar in the coffee, or Tony and Ronnie were both at the meeting. So let's visualize this. So we have 2 input units, input unit 1 and input unit 2. There's 1 output unit, just output, and the threshold is 2. And this models the AND. So we have Tony and we have Ronnie, and only if there's both Tony and Ronnie, we want the output unit to fire, to say yes, to say 1. So that's what we need. We need input unit 1 to fire to output unit, and input unit 2 to fire to the output unit. Then the threshold is reached. If only input unit 1 fires and input unit 2 doesn't, then we get an input to the output unit of just 1 and the threshold is not reached, then it will not fire. So we need to have both inputs or both outputs from input unit 1 to the output unit and input unit 2 to the output unit before it fires. And when is that the case? Well, if input unit 1 gets input, that is, it spots Tony, then it's an input of 1, and input unit 2 says, yeah, I'm looking for Ronnie. Ronnie is present as well. Now, then it gets input, it says yes, instead of no. No would be 0, yes would be 1. So in both cases it's yes. Then both input units get input. Both units will fire to the output unit, will send a signal to the output unit, and then the output unit reaches the threshold of 2. and sends an output. And that basically is yes. That is non-zero. Zero would be no output, and that would mean, just like with milk and sugar in your coffee, that there is either milk or sugar in your coffee and not both, or maybe none of them. So it just says no, they were not both present. Here's the output 1. That means in this case of the Tony and Ronnie detector, it says yes, Tony and Ronnie were both present. Now, what happens if there's only Tony? Then input unit 1 spots Tony, sends an input of yes of 1 to the output unit. There's no Ronnie, there's no input in input unit 2, therefore it doesn't send an output to function as an input to the output unit, and the output unit will not fire. There is no output, hence the answer is to the question, are Tony and Ronnie both present, is no. Of course, we could lower the threshold to 1. And then, I hope you see that, we have modeled the OR. Because now if there's an output from the output unit, then you know that either Tony was present or Ronnie was present. Because if Tony is present, then there's an input from 1 to input unit 1, and it sends a signal of 1 to the output unit, and then a threshold has been reached, and then there will be output. There will be output that says yes, someone was present. You don't know who, but it tells you that either of those were present, or that both were present. Because, of course, if Tony is present, then it will get this output. If Ronnie is the only one present, then only input unit 2 gets input and sends output to the output unit, and therefore the output unit also sends, because the threshold then is also reached. But the threshold is also reached if they are both present. So this is called an inclusive OR. It says one or the other or both. But the point here is, and that's why I use this example of these logical neurons, here you can understand what's going on. And here you can understand that if you lower the threshold, if you have this system and you lower the threshold from 2 to 1, that you have no longer modeled the AND, but you have modeled the OR. Okay. And you can also understand that you have to have a threshold of 2 if you want to model the AND. Okay, so this we can understand. Understanding why the systems work becomes really problematic when we look at our other examples. Basically, we can establish that they work, but we are left in the dark about why they work. So let's look at an example and how they train. This is an example to show you how they train these systems. So it's about detecting mines. So if you're in a submarine with no windows and you enter an enemy harbor, then the entrance of this harbor may contain rocks. Well, who cares? Don't come too close to them, don't bump into them, but don't come too close to them. But there might also be mines, and if you get really close to a mine, it will it will go off and it will sink your submarine. So you want to detect the mines with sound only. So these are actually these are the way to explain it in these lectures, but they really made these systems. So how could you recognize a mine from within a submarine using sound? Well, you could use radar. It didn't work really well. What you do basically when you use these simple, what you do is the following. You have a sound consisting of many frequencies, frequency 1, frequency 2, frequency 3, all kinds of frequencies. You send them all out with a signal strength of 100% of, say, let's call it 1. And then you measure what bounces off an object, a rock or a mine. And you do this in a lab prior to testing this in a real sub and a real enemy armor. You do this in a lab so you know, okay, this is what I get back from a rock and this is what I get back from a mine. So you send out all these frequencies, all with a strength of 1, and then you measure what you get back. So for frequency 1 with a signal strength of 1, you send it out, and you measure the signal that bounces back, and you say, well, apparently that's 0.3. I get back 30% of this sound of the strength gets back. You do the same with frequency 2, and you get 0.1 back. Frequency 3, you get 0.9 back, etc., etc., etc. And this gives you a set of values you can use as inputs for the input units. So in our example, we have a vector and it says, well, frequency 1 comes back with a strength of 0.3. So the input for our system, our connectionist network, in input unit A is 0.3. Input unit B gets 0.1. Input unit C gets 0.9, etc. That's the input. So this is how we generate the input. And if this is, in our first example, this could be what you get back from a rock. In a laboratory, you'll just measure what you get back from a rock. What the signal is, consisting of the strength of all these frequencies that bounces off a rock. So you use this as input for your connectionist network. In this case, it's been made. It had just 13 units as input, 7 hidden units, and 2 output units. Of course, you want the system to say something like, yes, this is a mine, so 1, and no, this is not a rock, 0. Or if it is a rock, you know it is the signature of the signal coming back from, then you want 0, 1. You want, no, this is not a mine, yes, this is a rock, 0, 1. So that's what you want. You just have 105 connections between those units. So what is interesting, I think, is that this is really simple compared to our brain. So what happens now? Because you have this simple neural network, 13 input units, they have connections to 7 hidden units, and these 7 hidden units again have connections to the 2 output units. But how do you get from this input of this vector we just saw to 0, 1 if it's a rock? How do we get there? Because initially all the weights are random. You set the system at random, all these weights. So these dials of your stereo amplifier, they are all set somewhere between 0 and 1. But, well, what happens to the signal getting in the system then? All these different inputs, how are they processed? What will be the end result? What will be the output? Well, if it's all random, it probably will be 50-50, right? Because, well, yeah, you get input in and output gets out, but if it's a random system, anything you put in will probably result in, well, both output units firing. So you have to train the system. You have to make sure that if you have in a lab the vector of the strength coming back from a rock, that it says 0, 1 and not 1, 0, because if you're then going to use it, well, it doesn't work. So you give a sonar input of a mine, and then you want it to be 0, 1, and for a rock you want it to be 1, 0, but initially both cases would be something like 0.5, 0.5 or 0.49, 0.51, something like that. It will be random. So what you do is you train it. You say, this is a lab, this is the signal I get back from a rock, I know this, so it has to be 0, 1. And initially it will be, say, 0.5, 0.5. How do we change that? Right, so this takes us to the next step, training the system. This works via backpropagation, and the idea is quite simple. The basics is the following. You have this system in which the strengths are set at random. So you have this signal of which you already know it's a signal or a vector coming from a rock. So you want it to be 0, 1 as output. And suppose the initial output is 0.5, 0.5. Now you just change one of the weights and see what happens then. So you change one of the weights, say between D and K, and you change it from 0.5 to 0.6, and then you'll see what happens. And if it then changes with the signal of which you know that it's of a rock, and you want it to get to 0, 1, if it now changes from 0.5 and 0.5 to 0.49 and 0.51, that's a change in the right direction. Then you say, ha, this is good. And then you stop, that is, you don't change that, you change another weight. And if it then goes to 0.48, 0.52, that's again in the right direction. So you leave it and you'll change another weight. If you then change a weight and you go back to 0.49, 0.51, you'll say, oh no, this is in the wrong direction. So you change it back and you change something else. And you just change that at random. Of course, there's a lot of work. So basically what you do is you get a classical serial computer to do this for you. And then in the end, you can have, of course, many signatures of different rocks and of different mines that you put into the system and you use as training data, and then you'll get, in the end, you'll get the right responses on the training data. Okay, so the system learns to detect mines. It makes a difference between mines and rock. So this goes step by step. And Andy Clark, a philosopher of cognition, calls this gradient descent learning. It's like blindfolded walking down a hill and finding the path. You just put one step in front of you, and if it's down, you say, okay, this is good. Then you take the next step. So you go step by step and you find your way down. And whenever you get a step up, you say, no, that's wrong, and you go back. And so it's really slow, and it's not something of which you knew the outcome beforehand. So when you're on the hill and blindfolded, you don't know which way to go. The only way is, well, you want to get off the hill, and you'll try to find a way down, but prior to actually doing that, you don't know what's going to happen. You only have the method of how to get there, but not the solution. Here too, you have this method of backpropagation, which is you have input and you have output, and then you look back to the input whether the output changed in the right direction. You know that it was a rock, so it has to go in the direction of 0, 1 to be an improvement, and otherwise you change your change back. The problem now is that this works, but that clearly we did not program it in a way that you say that we did with the logical neurons, that we said, well, okay, so we can design it, and if we do this, then we have designed a primitive network, a small network that models the and if we do it like this, we have modeled the or, and we could do that for many logical operators. And now we have this artificially intelligent device that can make a distinction between this sound signals of mines and rocks. but we didn't really program it. It's not that we said, well, between A and B, between A and D, the weight should be this, and between A and K, it should be this, and between C and K, it should be this. No, we just let a serial computer do the work for us, and then it turns out that you have a network that has certain weights between their units, and it works. And then Clark says, such learning algorithms, so used in this backpropagation, can discover solutions for the settings of our connectionist network we had not imagined. And it's also not the case that if you look at it and say, oh yeah, clearly, of course it had to be these weights. No, it doesn't make sense at all to us. It works. So that's what we can take home from this. There's something to be learned. Why does this work? But at least the interesting thing is that even such a simple network containing just a couple of units, that already works. Right, so we have an idea that connectionist networks work, and we know how we can train them. That's via backpropagation. Now let's make it a little bit more complex and then ask critical questions about it and see what we can actually learn from them. So still, it's all very simple. These days, so we're talking about the 80s when this was all developed. So, but we can learn a lot of it just looking at these simple neural networks. So back then, traditional AI was really good at mathematics and playing chess, for instance, but face recognition was a very difficult task, and we, normal human beings, are very good at that. So can we model that using connectionist networks? So Garrison Cottrell did develop such a network. It's not a complex system, and it performs very well and is really different from this classical serial approach to information processing. So let's take a look at it. So the idea is that we now have an input layer that is two-dimensional. So it can scan a picture. So it has a grid of 64 by 64. It's a couple of thousand units. So it scans all the different pixels, basically, of a picture, and it could see whether it is white, then it's, say, an input of 0. If it's black, then it's an input of 1. And if it's, well, some shade of gray, it will have the value corresponding to the shade of gray. Again, there's a hidden layer. In this case, it's 80 units, and the output units consist of 8 units, well, basically it says the first unit is for is it a face or not. So some pictures in the training set were of, say, ashtrays, so it has to recognize that as not a face. So it is either 1 a face or 0 no face. Then the next two were for a man and a woman. So unit 2 is 0 if it's a woman, and unit 3 is 1 if it's a woman. And then the last 5 units are a code, an arbitrary code for the name of the person, and in this case it's Janet. So the system is trained on that, and it works the same way. So you have the input, basically all the values between 0 and 1, from white via all kinds of gray to black, and the output should be, in this case, well, this is a face, it's not a man, and it is a woman, so that's the 1, 0, 1 of this vector, and then we have 5 outputs of the other 5 output units, 0.5, 1, 0.5, 0, 0. That's the code for Janet. So it should give that when it scans a picture of Janet. Again, via backpropagation, the connections were adjusted, so the weights were adjusted little by little, and in the end, is face recognition network worked. It achieved 100% accuracy on the training set of pictures. So whether it's a face or not, whether it's a man or a woman, and the name, so the identity of the person. Okay, so that is interesting. So it worked. Of course, you could ask the question now, could this have been an exact memory of the picture, so that you know that the system knows, okay, if this one is white and that one is slightly gray, it is 0.3, so if this is 0, if this is 0.3, if this is 0.4, so the exact numbers of input you get with this specific picture, that then it says 101 and then the code for Janet, so that it had learned this exact picture, basically the values of the shades of gray of this picture. So what you do next is you take a picture of Janet that will be slightly different, and we will recognize it as a picture of Janet, and use that as input, and then see what happens, because then the input differs slightly. And then the system had just one miss, and it was not just Janet, or other persons, pictures of persons as well. So it really worked well. It also performed really good on a set of pictures of new faces. Of course, it could not come up with a code of the name, because if you encounter someone in the Heuvelstraat here in Tilburg, you will also not know his or her name, but you probably recognize a face as a face and not mistake it for an ashtray. So the system performed really well. Now, one thing we should also be critical about is, well, okay, it worked. Apparently, it did not just learn the values of the inputs coming from the different pixels. It learned to recognize the faces of the people in the lab, and it was able to recognize faces and distinguish them from not faces. And now the question, of course, is, well, you have a picture and you leave it there. Was it not a kind of snapshot reasoning? Because, well, how much time did the system need? Time was not incorporated in the model. And of course, if we are walking in the street and you see someone, you respond immediately. So there is, you want a system that models the mind. Maybe Cottrell was not interested in that, but as philosophical connectionists we are, so then you want it to work in real time. Now, what you do is you add a loop. So what you do is you have input from the input layer going to the hidden layer and then to the output layer. Now, suppose this is like an eye. So there's input coming in the input layer. This changes constantly. And at some moment, for instance, you blink. There is no input coming into the system whatsoever. Now, does that mean if you blink with your eye that you don't know what you were looking at, or that you're surprised when you open your eyes and say, "Whoa, I did not expect that"? No. You just blink with your eyes and you expect the situation to be the same, because you have a kind of short-term memory, and if no input is coming from the outside world, there is still going on enough processing in your brain to know what you were looking at. So you shut your eyes, and then there is information going around in loops. So basically, what happens if you model it in our network, the hidden layer is now sending signals to a forward layer, and a moment later this forward layer is also sending the signals back without adjusting them to the hidden layer. So you make a loop from the hidden layer to a new set of also hidden neurons, but they don't fire to the output layer and they don't fire to the input layer. They fire back into the hidden layer. So you get a loop, a recurrent pathway. So that if the input layer does not provide new input, the hidden layer provides basically via this new layer the same output. You don't have to change that, but it provides you with the same input again a moment later. So you have recurrent pathway, and now you have built-in change, and you have built-in time, real time, into your system. And then these systems still work. So you can make sure they don't do snapshot reasoning. They can perform in real time. Okay, so that's a problem that has been solved. Let's look at the pros and cons of connectionism. When we looked at functionalism, we saw that in the end, even though it took science seriously, it took the mind seriously, it accepted multiple realizability, it was biologically not very realistic. Now we have connectionism. It also takes science seriously, it also takes the mind seriously. It also accepts, just like identity theory and functionalism, mind-body supervenience. Thus, the question now is connectionism indeed biologically realistic, or at least more realistic than functionalism was? And indeed, if we evaluate it, we'll see that it has some advantages over classical AI, even some advantages we were not aware of because we were not thinking about it as being problematic in the functionalist approach. And therefore we could in the end argue that indeed it is biologically a more realistic, or it contains a biologically more realistic model of the mind. So what happens is, and that's an advantage we were not thinking about, not really in such a way, it has an economical manner of representing. That is, if you think of it from an evolutionary point of view, if you learn something as an animal, if you have a neural network that's capable of learning, then in the classical idea, it would require storage. And each thing you learn has its own place in the memory. So you represent something you've learned, you're walking on the savannah and you've learned where there is where there's a pool of water where you can get something to drink. Then you have learned that, and you store that on your hard drive, to use a metaphor. You store it in your memory, and if you now learn that there is a second place somewhere else where there's also water, then you store that on a different place of your memory. Just like when we were looking at the Turing machine, we had this tape and we store each symbol on a different part of the tape. And in the end, that's not an economic manner of representing, because for everything you learn, you need memory storage. So there is this moment that your brain is full, and in order to learn something new, you should, well, have a bigger brain. Now, human beings do have quite large brains, but still, it's not an economic way of representing. If evolution via natural selection as an organism that does it in a simpler way, that is, maybe in a more complex way, but in a way that requires less energy, less physical stuff, then the organisms having that way of storing information would have an advantage over those doing it in a different way, in this non-economical manner. So what happens here is Where is the phase of Janet stored? Well, it's distributed over the entire system. It's not that you say, well, it's in unit K where it's stored. No, it's stored in all those units having these weights, having these connections. That's also the system where the phase of Garrison is stored. And that's also the phase where the place where the phase of a new member of the lab, the system has to learn the picture and the name of. Say his name is John. John is hired by Cottrell and his team. They make a picture of him. The system learns that. You don't need to add new neurons, no new artificial units. You just change the weights. And then it also knows the picture of, or it recognizes the picture of John and gives you the output. Indeed, this is a phase. It's a man, so it says 110 because it's not a woman, and then you have to attribute a code to John. So it's a very economical manner of storing data because it's distributed. You store different representations of the phase of Garrison, of Janet, of John, whatever, on the same, using the same units. You don't need to add storage space. So these representations are distributed over the entire system, and that's an economical manner of representing things. Big problem with functionalism was that it assumed that information is processed in a serial, step-by-step way, and if one step gets damaged, then the entire information processing is, well, gone. So if you have first step A, then step B, then step C, then step D, and step B doesn't work, then you won't get your output. So the system doesn't work. Now, if you have this neural network, let's say we're looking at unit A that sends information to units F through K, and the connection between A and K gets damaged. Well, there are still all the other pathways, all the other connections, and they still function. So A still sending a signal to the other units, and those units send signals to the output. So it's not that if one connection gets damaged, that the entire system breaks down. And what you see is that you can, if they've tried it, you can get rid of quite some connections or even units and still have the output you want. So it has high damage tolerance, which is biologically realistic, because if a neuron in our network gets damaged or neural connections get damaged or disappear, then we still function. It's not that we then break down altogether. So it's graceful degradation. It has a high damage tolerance. So we break down very gracefully, very slowly. So the system has high damage tolerance, and we have that as well. So in that case, in this respect, it is clearly biologically realistic, and is more realistic than functionalism, because then if there was some damage to a part of the system or a step in the system, step in the process, then it would break down altogether. A related point to the previous is that we get pattern completion in connectionist networks. So we just looked at what happened if there is damage to the system, then given some input you get the right output, if the damage is not of the entire system, but if there's some damage to it, you'll still get the right output. Also, if the input is slightly damaged, then still you get the right output. So you get pattern completion. The system fills in what it lacks in input. So if we look at a phase of someone we know and the eyes are blocked, for instance, then we'll say, oh yes, I still recognize this person. In this case, you'll recognize, yeah, obviously it's Tony. Now, with 1/5 of a familiar face to that system missing in a picture, then Cottrell's system would still recognize the face. So patterns are completed. That is an interesting thing. Basically, it says that if the system is slightly damaged or if the input is slightly damaged, you still will get the right output. And this means, also related, that we generalize. If you say we have this part of the input and usually that's Tony, then even though I don't see his eyes now, I still say, if I had to guess, that it's Tony. The same goes with new stimuli. If you have input, if you have trained a system on say panthers to recognize dangerous animals, and you use a panther to as a stimulus, pictures of a panther, and then you say, okay, the system has to recognize this as a big cat-like animal that is dangerous. Then, well, if you show it a tiger, then, well, it's really convenient that it will give you the same output. It's really convenient for you if you have been trained on panthers being dangerous, that when confronted with a tiger, you don't say, I've never seen that before, I don't know what I should do. No, it's really convenient. It's really better safe than sorry. They say, well, looks like it, probably also dangerous. And that means that we generalize. We are induction machines. And if you look at the Thinking About Science course, we now have something that's also biologically realistic, because all animals seem to be induction machines. What is interesting now is that this means that information is processed in our system in such a way that the input basically causes the output in all these via this parallel information processing. And if we have similar input, we have similar output. And in this case, it means that if we have the input of a panther, and you've learned to be afraid of that, then when you see a panther, you automatically will be afraid. You classify it as such, as a thing, as an animal you should be afraid of. The same happens with a tiger. That means the tiger has the same meaning. It is something you understand you should be afraid of, and you immediately do that. So what is interesting here is that semantically related items are represented by the same structure, by a structure that is very similar. And that means that we have at least a partial answer to Searle. We might not really understand why it's the case, but in our system it is the case that things that are semantically related are also syntactically related. And that was clearly not the case in functionalism, where you have all these separate representations on separate parts of the tape of the Turing machine, so on different parts of the system, so they are not related. And here we see that because of all the representations being distributed over the same system, you use the same units and the same connections to represent a tiger and a panther, that you indeed see that syntax and semantics are related. It's not a clear answer to how this works, but you can at least see that it is the case, and that this is, at least from that perspective, from the Searle's Chinese room argument against functionalism, here you can at least see that there is a start being made by recognizing that in this case syntactically related representations are semantically related. So all in all, connectionism is biologically indeed much more realistic than classical AI, and we can already see this from these really simple systems. And these days, of course, connectionism is much more complex, but we can already see this. And one of the interesting things, of course, is that, well, these systems have high damage tolerance because of the representations, the cognitive states, being distributed over the system or over a part of the system. If you get larger complex systems, then you'll see that different representations get distributed over part of the system, but still they use up a lot of neurons and connections. So you can say that representations are stored in are distributed over that part of the system, making it very tolerant to damage. And also you'll see that you get this free generalization, you get pattern completion, and it also means that these representations, well, they are not discrete entities. Right, let's look at two possible counter-arguments against the claim that connectionism is biologically realistic, a biologically realistic model of the mind. The first one is based on the systematicity of thought, and the second argument is that if it is biologically realistic, then eliminatism follows with respect to propositional attitudes. And the counter-argument, of course, is then that you don't say, well, propositional attitudes don't exist, but you can argue that it's not biologically realistic. So let's take a look at the first argument. Thought is systematic, it's rule-based. So that's an important property of linguistic thinking. So if you say that the Eiffel Tower is bigger than a Martini Tower, and we're not going to debate semantics here, so that I suppose you know what the Eiffel Tower is, what the words mean, that you know what the Martini Tower is, then obviously the Martini Tower is smaller than the Eiffel Tower. Or if you want to use all, in two sentences, all the same elements, then you can say John visits Jane and Jane visits John. So there's a system to it, there's a systematicity to it, there's a rule to it. If John visits Jane, you're using the same words in a sentence as Jane visits John, but since the order is different, it has different meaning. If John says, I'm going to visit you, Jane, then she stays at home, right? And if Jane says, I'll visit you, John, then John stays at home. So thought is systematic. We think in language, and if we do so, then we basically compute, manipulate those elements according to certain rules. And when you change the rule, when you change the order, the rule says that the meaning changes. So now, where do we find this in connectionist networks? Well, Fodor and Piligian say, no, we don't find this in neural networks. So if you don't find this in neural networks, because, well, we don't have these separate elements, and we don't have thus the elements we need for the rules to manipulate them, then it can't be a good model for cognition, because we need those elements and rules so we can think orderly, we can think systematically. Okay, well, the question, of course, is this a convincing counter-argument? Because the idea then is, well, we think in language, we think rule-based, we need these elements, and these elements are not present in the connectionist networks. Thus, it is an incorrect model of cognition. It's not biologically realistic, because we do think in language, we do use these words, and our thought is systematic, is rule-based. Now, is that convincing? Well, I would say not, and I'm not the only one, of course. The idea is that if you look at mind-body supervenience as realization, then what is realized is in some sense different than the realization base is. If you're an identity theorist, then you say, well, if a mental state is identical to a certain brain state, then all the properties of this certain brain state are properties of the mental state and vice versa. But if you say, no, 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 it's not identity, it's realization, mental states are realized by brain states, or they could be realized by something else, then that was an argument against identity. But then that means that mental states can have properties that the realization base, be it a brain, be it a computer, does not have. There should at least be one thing different, whatever that is. So it could also be that these elements we have in our mind, these words, these concepts, if it's at all true that we think in language and we think in a rule-based way, if so, let's suppose for a moment that that's true, that is the way our biological system works, our biological mind works, then still it could be the case that it is at this higher level in our model of the world that we find the systematicity that we don't find in the realization base. So that is basically an empirical question. Why would you a priori think that the property that is realized in the mind is also a property of the realization base, that you find the same systematic structure in the language that apparently is in our mind? Why should that also be in the realization base? Maybe it's possible to use a connectionist network that thinks in a systematic way. Why not? Well, I don't see an a priori argument against it. So it's a wait and see approach we should have here. And then it turns out, well, it actually has turned out that we have, scientists have made connectionist networks that actually can learn natural languages. So clearly a naturalistic, a natural language, a language with words, can be learned by a system that is not systematic in that way that language is, that linguistic thought is. So it looks like that indeed the argument doesn't go. So it's not very convincing, to say the least. The second argument is starting from the assumption, so okay, if connectionism is indeed a model of the mind, is the model of the mind, then the elimination of propositional attitudes follows. And that's why I started this this lecture with a brief recap of what propositional attitudes were. So propositional attitudes are stances we can have towards the meanings of sentences, attitudes we can have towards propositions, and they are functionally discrete entities. So that means you can learn or forget a propositional attitude without any influence on other propositional attitudes. Just like the beans in the bag. If you put one extra in, it doesn't do anything to the other beans, and if you get one out, it also doesn't do anything to the other beans. So you can learn or forget a new propositional attitude. You can put a new one in your mind and you can get one out of your mind and it doesn't do anything with the other propositional attitudes. So if propositional attitudes need that. So then it would mean, in this classical idea of functionalism, that they all need a separate part of the Turing tape, the tape in the Turing machine, or a separate part of the storage device, or a separate part of the memory of well, whatever device you have, piece of paper, a computer drive, a tape like in the example of the Turing machine. And then you could indeed erase a symbol and replace it with something else, and it doesn't do anything to the other symbols that are stored in the system. But now we have seen in the example of face recognition, for instance, you have the system, the realization base is this entire system, and it realizes an internal mental state, a cognitive state at least, maybe not an experience, but at least it represents something. It represents, for instance, Jane's face or John's face or Garrison's face. And it's the same system that represents Jane's face as does represent John's face. And we said, well, John was the new employee and the system had to learn his face. And then we had to change the weights of the system. Thereby also, you also change the weights that realize the internal mental state, if presented with a picture of Jane, of, well, Jane. So that changes. If you would make so many, if you had a lot of different new people and you change so many weights time and time again, then, well, you might forget who Jane is. Not because it's deleted from this part of the hard drive or this part of the tape or something like that. Now, you have changed the realization base of the concept of Jane if you do that. So that means that propositional attitudes are not discrete entities. They are intertwined. They are realized by the same base. And that means that if you change something to the realization base in order to store a new propositional attitude, that is a new belief, a new mental state that is about something, then you change others as well. Or at least you run the risk of doing that. So that means that propositional attitudes in this classical sense do not exist. There are no such functionally discrete entities. So if I learn that cats have paws, that's one of the examples these people debating this are giving, then you learn, if you first learn that cats have paws and then learn or forget that dogs have paws, so first you learn that and then you unlearn that, the entire connectionist network changes. And that means that also the other representation slightly changes. And maybe if you change the weights a lot, then it changes a lot. So that means that propositional attitudes in the classical sense cannot exist and thus have to be eliminated. They are part of our folk psychology or of our philosophical theory about the mind, but they don't exist. That's not to say that beliefs don't exist, but we have to think in a different way about beliefs and knowledge and hopes and those mental states that we, in our initial classification, would classify as propositional attitudes. Right, so the first two counter-arguments are not that convincing. There is one that is convincing according to many, and that is not only an argument against connectionism, but also applies to the identity theory, at least to the mind-brain identity theory, maybe not to the mind-body identity theory, and functionalism, because all those theories seem to look only at the brain as the realization base for mental states. So they all accept supervenience. Mind depends on the physical world. What part of the physical world? The brain, or in terms of functionalism and connectionism, it could also be an artificial brain, but you're not looking at the body. And that is wrong according to many philosophers and scientists, maybe there's more to the supervenience base of the mind than just the brain or an artificial brain. So that's also a problem, of course, then for the identity theory, if interpreted in this way. It's usually interpreted as a mind-brain identity theory and for functionalism. So we'll need to take a look at that. Connectionism is a contemporary view on the mind-body relation. We've come a long way since substance dualism, and connectionism indeed seems to be a very good theory for answering the question how the mind fits in the physical world. It's biologically more realistic than functionalism. It takes science seriously, it takes the mind seriously. The only problem there seems to be is that it is a brain-centered theory, and the suggestion is that the supervenience base might be wider than just the brain, so then connectionism doesn't look at the mind in the broad perspective it should. How can we interpret this idea that the mind might have a supervenience base that's wider than just the brain? Well, we'll look at the embodied theory of the mind. It says that the body is partially relevant and determining the mind, or even the situation in which you are, so the circumstances in which you are in. So that is what the embedded theory tells us. And it could even be the case that there are parts outside the brain and even outside the body that could or should be regarded as part of the cognitive mind. So that is what we'll take a look at next when we try to answer the question, how does the conscious mind fit in the physical world?
That's it for lecture 5. Stay safe.